All right, let's get started. Hold on, let me make sure. Give me one sec. Oh. Is my mic on? Yep, my mic's on. Sorry. Okay, so let's get started. I only have one announcement, but I do have something I want to mention about homework number 4. So first off, it's due on Friday, and I know some of you are probably thinking, here's the deal, Dr. Mike. We got a celebration in this class after this. That guy is a jerk. Well, I'm going to make your life a little easier by giving you this hint. I kind of already gave it to you on the homework assignment, but I wanted to do this to help you out. So, for example, and I'm going to draw here on the slide to kind of explain what's going on. Okay, I got a beam. And it's 20 foot long. And it has 60 kips on it. And you say, I know what I'll do. I'll take this and I'll just sort of, you know what? Let's just do this. And we'll say it's 3 kips per foot because it's 60 kips over 20 feet. And we'll use WL squared over 8. And if you do that, I'm going to say, do me a favor, take the hand like that. No. This WL squared over 8 only works if this is your loading, okay? It only works if that's your loading. So if you have this loading scenario, it doesn't work at all. Remember, if you have a point load, what does your shear diagram look like? It goes up and over and down and over and up. So your moment diagram is linear. This is when your moment diagram goes like that. So this is why you have like a parabolic term, like the WL squared. So if you have this type of loading scenario, or any loading scenario that's not this, WL squared over 8 does not work. That's not the formula that you use. What we did on a lot of our example problems is this, is we had like a W dead and a W live. And what we did is we say, okay, let's determine a WU. Let's take that and determine a WU, and then take that and determine an MU. Okay? The hint that I gave you on the homework is this. You're going to have, like a W dead load, and you might have some point loads, let's say some live point loads. And so what I propose that you do is handle each of those separately. Determine a dead load moment. Determine a live load moment. And then say MU is 1.2 dead plus 1.6 live. Okay? So I'm telling you that now because I've actually already seen it happen. I've had some students ask me some questions about the homework assignment, and they were doing this. I said, no, that doesn't work. So the WL squared over 8 only works if that's your loading scenario. I think problem 2 is like a cantilevered beam, right? So it doesn't even work for the dead load on that problem. Now, I gave you that guide, that aid on Blackboard where, you have shears, moments, and deflections for a series of different loading scenarios. So use it. It's there, And I don't have any problem with you using it on homeworks. I don't even have a problem with you using it on exams. I've been known to put relevant, formulas and values on the exams. I don't have a problem with that at all. So, because this isn't structural analysis, this is reinforced concrete design. You've proven to me that you can draw shear and moment diagrams, otherwise I wouldn't have let you out of 312 last semester. So I don't have an issue with providing you that support, but at the same time, use that support, okay? So, any questions? So there's that. So today, what we're going to do is we're going to go through this design example on one-way slabs, and then we're going to go into flange sections. Now remember, one-way slabs, that's it for exam 1. Once we're finished with one-way slabs, we are done with exam 1 material. But before we do that, though, I kind of wanted to show you something. You can go away. Here, let me mute that. Okay, I want to show you something. It doesn't have anything to do with the announcements, but I kind of wanted to show you this. So if you have your example 6 calcs, pull them out. I want to show you something. So do you remember example 6? That was our full-blown start to finish Reinforced concrete beam design example. That was the unknown cross-section problem, right? So we had to start from scratch, okay? And so when it was all said and done, what did our beam look like? We had a 4 KSI beam. We had we had 4 KSI concrete, 60 KSI steel, and what did we end up with? We ended up with a beam that was 14 inches wide. It had an effective depth of 21 inches, and the area of steel was 3.82 square inches, and it was 3 number 10s, right? Everybody remember that? That's what we had at the end. And then we got into a discussion about, well, what happens if we start, what happens if we want to improve the efficiency of the beam? So the beam efficiency was 91.2, so it was good, but we could probably do better, right? And so how did we end that discussion? We said, well, there's really 5 parameters that we can change. And there's these 5 highlighted parameters up top. We could change the FC prime, we could change the FY, we could change the B, the D, or the area of steel. Now, I want to show you a couple things on this spreadsheet. I draw your attention to the formula bar up top. So for instance, other than these highlighted 5 values up top, everything else is sort of smartly being calculated. So for instance, the height of the beam, see how it's saying it's the depth plus 3 inches? And then we have the self-weight of the beam. So it's taking the area times 0.15, dividing it by 144 to get kips per foot. It's factoring the load and WL squared over 8. It's doing, the A calc. Look at the beta 1. The beta 1 is even, interpolating the, if it's between, between 0.85 and 0.65, it's interpolating to determine that. So it's actually figuring out the beta 1. It's determining C. It's determining the strain of the seal. It's doing all of this stuff smartly. So I can start changing values, and I can, look at the effect. So let me show you something. Remember how I said that FC prime really doesn't matter? Watch this. Look at your efficiency. Okay? Watch what happens when I double the FC prime. Like it's 4 KSI. Watch what happens when I make it 8. Really doesn't change the behavior of the beam all that much, does it? I mean, we doubled the FC prime, but look at your FEMN. It went from, so watch this. It went from 320 foot kips to 340. So you double the FC prime, and it really doesn't affect things that much, does it? Now watch what happens if you make, watch, here's another one. Let's say B. Okay, we have a B of 14 inches. Watch what happens when you make B 16 inches. All right, you know what? Yeah, let's 16 inches. It hardly doesn't change anything at all, Like it's very, very insensitive. But watch this. See the depth is 21? Watch this. What if I make the depth like 24? Bam. Significant jump, right? Went from 319 to 371. That number changed a whole heck of a lot just with a few inches. Remember how I told you the depth is very, very, the strength of a beam is very sensitive to a beam's depth. Whereas if I make this like 10, it really doesn't hardly change anything at all. It's really insensitive to that. Same thing with the area of steel. Like if I take the area of steel from 3.8 to make it like 4, I mean that's not very much. Only 0.2 square inches of steel, and it's very, very sensitive. So I'm sure you're probably thinking like, are you going to give us that sheet? No, I'm not giving you that sheet, but I do honestly recommend that you look at something like this, look at creating something like this, and it's really interesting to see what happens. Like for instance, theoretically, if I doubled the FY, you would think that the capacity of the beam would go up like crazy. Well, that's actually not the case, because while the MN, might go up or something like that, we don't meet our strain limit, and we end up having a really, really low phi value, so it actually is no good. So, it's kind of interesting how some of this stuff works out. So it's just something I just wanted to, show you and sort of play around with. In the end, if you need to iterate, I would iterate either your depth or your area of steel. I'd probably start with the area of steel. I'd pick your next iteration if for some reason it's not strong enough. So yeah. Although the real first step, since you're students and you're learning the design process, the real first step is to check your math. Because more often than not, if you're in design land and you do some math and you get a beam and it doesn't work, you might want to check your calcs. If your calcs are fine, then you need to start iterating, and your iteration should probably start with the steel, like change the steel pattern. Everybody okay with that? All right, any questions?
We also talked about adding up the decreasing the load.
Yeah, and you could do that. No, I didn't set up my sheet for that.
That's what I was going to ask, if that would be something like, that would be feasible to add into a sheet like that.
Oh, of course. What I would do, what would be a little bit more feasible, is instead of trying to change the load, because you can't really change the load. I mean, changing the load would be saying, well, we're not going to design a library today. We're going to design a hospital. But what you can do is change, let's say, the girder spacing. Because changing the girder spacing would change the tributary area, which is going to change the live load reduction, which is going to change the live load on the beam, which is going to change that. So
now doing that would also...
The sheet would get bigger.
Well, and it would decrease the numbers we needed for those specific records, right?
Yes.
Yeah.
So that would be the way I put it. So when you say decrease or increase the load on the beam, it's not really that you're changing the load on the beam, but what you're changing is the amount of floor area that beam is responsible for. That's something that is within your purview. So, are we okay with that? Okay. And so yeah, one other thing I put in the sheet, I put a check on does it meet the minimum steel requirement, does it meet the 0.004 strain requirement, and does it meet capacity, so if VMN greater than or equal to MU. This is Excel. This is not a hard sheet to build, so I just, for practice, I mean, I would consider this a somewhat worthy exercise. Okay. All right, let me go back to this. Okay, so we're in slab land. So remember, let me go back a little bit. Remember, the design of a slab and the design of a known cross-section are very, very similar because you know the width of the cross-section. We assume that the slab goes on forever, and we just cut out a strip, and usually we take that strip to be a foot wide or 12 inches wide, and we say, okay, whatever reinforcement I need in that strip, I'm just going to repeat it across the slab, and there's my design. As for the height, we take the height off of the minimum thickness requirements from ACI. This is the previous design aid that we were using earlier. And there you go. So the structure, or the cross-section, the dimensions of the cross-section, they're known. So it's a known cross-section design. So we use the rho value that was a little bit more complicated. We use that same rho equation, but again, it's a little more complicated because we can solve for rho. It's not like we're just picking a value out of the sky. We know the B, we know the D, we know the material parameters, we know MN required, so we can just plug and chug and solve for rho. So it's a little bit more intricate. We do have to assume a phi value, so when it's all said and done, you need to verify that. The only thing that's different other than that are three things. One, your moment requirements are a bit smaller. So if you get a bending moment of like 10 foot kips, that's okay because you're talking about a slab. So the tributary area is very, very tiny, and you're only talking about a beam that's this big. So it's okay if the moments are small. That's okay. Two, you are not sizing one set of reinforcement. You're sizing two. One being the main steel, the actual steel required for the strength of the section. Then you're also sizing the temperature reinforcement. Okay. The third is this. Okay. So if you go to Blackboard, if you go into the design aids section, there's the shear moments, there's the beam design aid, and then there's the slab design aid. So I'm going to pass this out. There you go. You all have this online, so it's not like I'm giving you anything you don't have access to. I just wanted to give you a hard copy for today. Oh. Oh, sorry. Okay, so this guide, I don't want you to think, so this is supplement number 3 on Blackboard. I don't want you to think that there's anything mysterious behind what's going on in this guide, because there really isn't. It's a really straightforward design guide. And I actually want to show you how it works. So the easiest way I'm going to show you is I'm going to look at number 9s. Okay? So what is the area of a number 9 bar? 1 square inch, right? Okay, so let me do this. Zoom in a little bit so we can kind of see what we're looking at. Okay, so looking at this number right here, I want to look at the number 9, and I want to look over here. Okay, so over here on the left, it says this is the girder spacing, or not girder spacing, it says the bar spacing, and it's saying the bar spacing is 12 inches. Does everybody see that? So what this entry is saying is that if I have number 9s and they're spaced every 12 inches, then I have 1 square inch of steel per foot. Make sense? Now, what happens if I decrease the spacing to, let's say right here to 6 inches? Well, if I have a bar every 6 inches, how many bars do I have per foot? 2 of them, right? And so as the bar spacing decreases, the amount of steel per foot increases. Make sense? So that's all this guide is doing, is it's taking the area of a single bar and it's saying, well, if I take that single bar and space it 6 inches or 4 inches, how much is that per foot? So for instance, if I space number 9s every 4 inches, that would be 3 bars per foot or 3 square inches per foot. And so that's how this is computed. So all you're doing is taking these values, multiplying them by 12, or taking the areas of bars, multiplying them by 12, and dividing them by whatever this is, and there you go. So everything across this row here where it's 12, those are just the actual areas of the bars. And so as the spacing goes up, the area goes down, and vice versa. That's it. So does that make sense? I don't want you to think that there's anything like super mysterious about this. There really isn't. But this guide is much more appropriate if you have a pattern of reinforcement that you'd like to repeat over and over again, like in a slab. So, okay. Okay, so with that, I'm just going to go ahead and shut up and get right into it. So we're going to design a one length is 10 feet. Now remember, when we're talking about slabs, the span length of a slab is the spacing of the beams. So how far apart the beams are is how far apart the slab needs to span. It has normal weight concrete, 4 KSI concrete, 60 KSI steel. We have a live load on here that's 200 pounds per square foot. This is a hefty load, to say the least. So we have a pretty hefty live load on here. The only dead weight is the self weight of the structure. So no superimposed dead load on top of that. And so we're going to design accordingly. So excuse me. All right, so with that, let's just go ahead and get right into it. So I'm going to do a little bit of artwork here, so please forgive me. I'm going to also try and remove this. There we go. Okay. So here's sort of what we're after. So forgive me if my artwork is horrible. So I've got, let's say, 2 beams, and I have the slab on top of those beams, okay? And what's going on is this goes on, forever. So it goes on sort of like that, okay? And when we talk about span, we're talking about the span length of the slab. So we're talking about the girder spacing of the beams being 10 feet. Okay? And what we're doing is we're saying, okay, I want to isolate a strip of that slab, and that's what I want to design. Now, the width of that slab, we're taking that to be 12 inches. Really, it could be anything. We could take whatever width we want, but 12 inches is easy because that's a foot. So we're figure out the reinforcement per foot and just repeat it, okay? So if we look at our beam, this is what our beam looks like. So if I'm looking sort of like this, that is the best you're going to get. Oh, and if you make fun of my drawing, we're going to have some problems.
I think you should just start drawing. And that's still the best way to start.
Well, thank you. Thank you. So if you look at, so if we're standing on this side of the beam looking like this, I want to look at sort of this cross section. Okay, and so this cross section is this sort of red shaded region right here. And so what I'm saying is there's a couple things already figured out. We know the width. We know this is 12 inches. Okay? All right? And so, oh, actually, hold on. Sorry, I want to move this down here. Sorry. I'm going to put this down here. Sorry. Okay? Because what's going on is just like this. Remember, this sort of goes on forever. So this cross section sort of goes, well, it doesn't go on forever. It only goes for 10 feet. But it goes like that. Okay, so we know the width, but there's a couple things we don't know right now. We don't know the height. We don't know how tall, or in this case, how thick the slab is. We also don't know the dimension from the top of the slab to the effective depth where the rebar is going to be. Okay? So that's going to be, you know, this dimension here. Now I'm putting like 4 bars of main reinforcing steel, but it could be 4, it could be 6. I have no idea. We're in design mode. So ultimately, though, we're going to have 2 patterns of steel. We're going to have a pattern of steel that goes along the span, you know, something like that, and that's the main steel. Okay, so that's the main steel. But then we're also going to have temperature steel that's going to sort of go in the opposite direction. So we're going to have to size both of them. So if you want to compare that over here, the main steel goes from beam to beam, whereas the temperature steel sort of, I guess if kind of want to look at it like this, kind of goes in and out of the screen, kind of this way. All right? Does that make sense? And again, we need temperature steel for slabs because of their inherent nature of being so thin. We don't really have to worry about that with beams because beams have all sorts of reinforcement that you're going to understand after we're done with the class, because there's the tensile steel for bending, there's the stirrups for shear, a lot of times there's compressive steel. So there's a big rebar cage inside of beams. We don't have to worry about it, but for slabs, we got to throw that extra layer in there for shrinkage and, you know, heat, you know, getting hot and getting cold, wanting to crack, so on and so forth. Sound good? So I kind of think this exercise is kind of necessary to just make sure we all understand what we're looking at. Okay, so step 1 is always to compute our factored moment. Okay, now let me scroll down a bit. Okay. Now, we know that B is 12 inches, okay? Now, our height is going to be our minimum height, which comes from ACI. So anybody that has their slides in front of them, for slabs, for a simply supported slab, what is that going to be? So we're going off right here. So a solid one-way slab, simply supported, L over 20, right? So we're going with L over 20 right here. So that's L over 20 which is 10 feet over 20. However, let's convert that. And so what does that come out to be? 6. So this slab, we already know it's going to be 6 inches thick. Okay? So here's another thing, just right off to the side. Note. So unless otherwise noted, like unless you're told otherwise, take the D to be H minus 1. See, with beams, you got a lot more going on. You need 1.5 inches of cover. You got your stirrups. There's a lot more stuff there. So 3 inches makes a lot of sense. For slabs, the cover requirements aren't as stringent, and the bar sizes are usually a bit smaller. So unless told otherwise, take your D to be H minus 1. That's a little bit, I say we're skirting a little bit close to the edge, but that should be pretty good. Yes?
How do you know that you
That's a good question. The reason is because for slabs, your cover requirement is a lot less stringent. See, for beams, we had it a 1.5 inch cover requirement. For slabs, we only need 3/4. So we only need 3/4 of cover as opposed to beams, so our cover requirements are a lot less. But 3/4 of cover, that's to the edge of the bar, right? And so when we compute a D distance, that's to the center of a bar. You see what I mean? So upping it a little bit makes sense. I've seen folks use 1 inch, and I've seen folks use 1.5. I would not go more than 1.5. That's a bit extreme. So, and with slabs, you want to use every available inch that you can because you don't want to have to make the slab thicker, because making a slab like a 1/2 inch thicker, that affects the entire building. Think if this slab was like 1/2 inch thicker across the whole building, how much extra weight would that be on the building? A lot, you know. So you want your slabs to be as thin as humanly possible. So, all right, does that make sense? All right, sound good? My phone been going off? I'm like a popular guy here. What's going on? All right. So because we know the dimensions of the beam, we can go ahead and compute W sub naught. How do you compute the self-weight of a beam? Pop quiz. We've done this before. The unit weight times the area, right? So gamma times B times H. So gamma C, BH. Anybody got a problem with that? Right there? The units don't match. So the unit weight is in cubic feet. So let's convert these to feet. So we're going to divide by 12, but we're going to divide by 12 twice. So really what we got going on is a square foot, 144 square inches. And so what does this come out to be? Say it again. 75 pounds per foot, right? And so this is actually kind of serendipitous because you have a section that's 12 inches wide. What if it was 12 inches tall? So the area would be 1 square foot, right? So the area is if the area was 1 square foot, then the weight per foot would be 150 pounds per foot. But this is 1/2 square foot because it's 12 by 6. So what's 1/2 of 150? 75. So that's a really round, convoluted way of doing 150 over 2, but that's basically what we were doing. Sound good? Now, how do we determine the live load? Like, what's going on there? Well, we do that in a very similar fashion to what we did on, let's say, homework number 1. What is the live load specified on this problem? It's 200 pounds per square foot. So what I'll say is this. For a 200 PSF live load, I'm going to say that WL is 200 pounds per square foot applied over the tributary width, right? What is the tributary width for this 12-inch wide beam going to be? 12 inches, right? This slab up here, this strip of slab is going to be responsible for that. So there you go. Now I can hear some questions already brewing in your head, so we're going to address that here in a second. But hold on. We have 200 pounds per square foot applied over 12 inches, but we'd have to convert that. So that's 1 foot per 12 inches. But that's sort of silly because I can do that math. That's 200 pounds per foot. Right? Now, I can hear that question brewing in everybody's head, and what's that question y'all want to ask? What about live load reduction, right? What about live load reduction? Dr. Mike, there's a live load. You didn't talk about live load reduction. Shame on you. Well, there's a couple reasons why we would not perform live load reduction on this problem, and I can think of 2 of them right off the bat. Number 1, you only perform live load reduction whenever your live load is less than 100 pounds per square foot. We are certainly not the case here, right? This is a super heavy live load. But some of you might be thinking, well, Dr. Mike, that's a cop-out. What if it was 80 pounds per square foot? Well, you still wouldn't apply a live load reduction, and here's why. Let me scroll up something fierce. This is our equation for live load reduction, right? Remember that? So live load reduction does not apply for the following. And let's look at this first bullet point. This is basically saying that the influence area has to be greater than or equal to 400 square feet. In other words, you don't apply live load reduction for members where the tributary area is really tiny, right? So what is the tributary area for this slab? For this strip of slab? Well, the tributary area for this strip of slab is 10 foot by 1 foot. It's only 10 square feet. So this slab has a very, very small tributary area, so we wouldn't apply live load reduction anyways. Okay? So does that make sense? So I did really want to address that because I didn't want to leave that thread sort of dangling throughout the semester. So you never apply live load reduction for slabs because of the amount of floor area that it's responsible for. It's very, very tiny. Sound good? So now that we got that, we don't have a superimposed dead load, so it's just this. Okay, and so that equals what? Say it again. 410. Do I have a second on that? Okay, and so MU, here, let me scroll this down a bit. I'm running out of room. MU is W sub U L squared over 8, and so that's that equals what? Now remember, WL squared over 8 still works because we're still considering it to be a simply supported beam with a uniformly distributed load. So that still is appropriate. 5125. Now what are the units? No. 5125 foot pounds because we're still in pounds per foot. So what would this be in foot kips? So what did I say earlier about the moments being tiny? That's going to happen. That's okay. When you're looking at slabs, you're usually dealing with like 5 foot kips. Like it's really tiny. That's okay. Don't let that freak you out. So Because I know when you're doing homework assignments and it's like you expect this number and you don't get it. And so usually it's easier when you know you did something wrong, but when you can't figure out what you did wrong and the number still doesn't look right, doesn't that just get you when you're doing a homework assignment? So that's what I'm saying. That's okay. That's tiny. Okay. It's like I've been a student before or something, right? All right, does everybody have this? Okay. So let me scroll down a bit. So this is going to be pretty familiar from here on out. So step 2, compute our required MN. Remember, we need to assume a phi of 0.9. So when this is all said and done, we're not going to do this in here, but when this is all said and done, you would need to verify this. So MN required is MU over phi. So remember, phi MN has to be greater than or equal to MU, so that's how we get that. So 5.125 foot kips over 0.9. And so that equals what? Foot kips, and then go ahead and multiply that by 12 to give me that in inch kips. .33. Okay. And so what's step 3, if you're following along? We got to compute what? There you go. And so this is the nasty one. All right, so it's 0.85. FC prime over Fy, 1 minus 0.85 FC prime BD squared, 2 MN required. And then clean that up a bit. 4 KSI concrete, 60 KSI steel. Then we have our B is 12 inches. What was D? There you go. Remember, row values are tiny, so it's okay if this comes out small. Say it again. You might want to check that. I got something way different. Did you square your D? Excuse me, I'm sorry. So 0.00393. Did anybody else get that? That's the answer. So here, I'll sort of underline that. I'll give everybody a second on that because it looks like everybody's still writing. So. All right. Everybody good? Any questions? I mean, am I going too fast or? Okay. All right, so if you've got that, that's not what, there we go. All right, so we're going to compute required steel areas. Okay, so when you're doing slabs, okay, there are two areas of steel that we need. We need an AS required, and we need an AT required. So main steel and temperature steel. Now, I want everybody to pay attention to this. How do you compute the AS required? It's rho BD. Now, here's the thing. How do you compute AS required? 0.0018 BH. That is not a typo. Okay? This is a very easy mistake to make on the exam, to just do rho BD and 0.0018 BD. No, 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 no. The spec defines our temperature steel requirement as a function of B and H, not B and D. So don't mix up the two. Okay? So okay. And so let's take the top one. What do you get? 0.236. Do I have a second on that? Now watch this, watch. That is square inches per foot of slab. What about the next one? So maybe 130. Okay, sound good? All right. Okay, now step 5, we need to select our reinforcement. But before we start looking at this, I want to show you something. All right, let me go back here. What slide were we on? We were way ahead. Okay. When you're doing slab design, so you need to select, your patterns of main reinforcement and temperature reinforcement. Before, when we selected patterns, like what we would do is we would say, okay, here's our area of steel requirement. Let's pick a couple choices, and then for each of those choices, we would ask whether or not it fit, right? Well, whether or not it fit doesn't really apply to slabs because the width is theoretically forever, right? So that's not really an issue. What is an issue is the bar spacing. See, theoretically, you could come up with an economical bar spacing. Like you could take number 18 bars and put them every 12 feet, and that would work. But that's not really very smart, right? Because you'd have 12 foot of slab with no reinforcement in it, right? So there is a limit on the maximum bar spacing that you can choose. Usually it doesn't matter, but sometimes it does. So for main reinforcement, it's the lesser of 3H in 18 inches. For temperature reinforcement, it's the lesser of 5H in 18 inches. It's a little more stringent on the main reinforcement because main reinforcement is trying to ensure that the slab doesn't fall and kill people. The temperature reinforcement is just trying to ensure that it doesn't crack under, thermal changes and shrinkage and things like that. So, excuse me. So for main steel, S max is the minimum of 3H and 18 inches. So that's the minimum of 3 times 6 inches or 18 inches. And so what's the minimum? It's the same, right? It's 18 inches. And so S max for the temperature reinforcement, for the temperature steel, is the minimum of 5H and 18 inches. But 5 times 6 is 30, so that's going to be 18 inches as well. Sound good? So now what I want you to do, now first off, is that going to matter for any of these choices here? Exactly. So it only goes to 18, so it's not really, we can pick pretty much whatever we want. So what's our area of steel requirement? 0.236. So does anybody see any patterns that we could use that's just a little bit larger than that? How about number 4s at 10 inches? Does everybody see that? Number 4s at 10 inches would work, right? What about number 3s? Is there a pattern that could work for number 3s? 5.5, right? And these are pretty economical. Is there anything else that's in the 0.24 range? Because think, you want to get above 0.236, but just slightly above. Anybody see something else that's going to work? We could do that, but that's a little bit bigger, right? You got what, 0.25? So if I was going to go between the 0.25 and the 0.24, I'd go with the 0.24, right? Everybody okay with that? Now, of these two, so there's number 3s at 5.5 and number 4s at 10 inches. Which one would you use because they're the same area? And why would you do that? It's the same area, but it's less bars, less stuff to handle. So I propose use number 4s at 10 inches for the main steel. What about the temperature steel? Anybody got a good option for the temperature steel? What about number 3s? Is there a good option for the number 3s? 10 inches. What about for the number 4s? 18. Anything else that would work? Not really, right? Everything else is going to be much bigger. So which one would you use, the number 3s or the number 4s? Number 4s. So use number 4s at 10 inches for the main steel and number 4s at 18 inches for the temperature steel. Well, it's usually spec'd out in the drawings that they need to play. That's a fair question, and the short answer, if we're talking about structural changes, then the contractor needs to reflect those structural changes to the engineer. And if not, then that's how you get Hyatt Regency, what we talked about in steel design. So yeah. Now, I say that this is the answer, and spoiler alert, it is, but there's one thing that we forgot. Fee should be verified. Okay. One super final note I'll mention about slabs. If you compute their efficiency, like their MU over phi MN, they're usually really high, like 98, 99%. They're usually really efficient. So they're not like beams where you can get like a 90, 91, 92. They're usually really on the money. Because look at this. Look at, here's the requirement, and look what we picked. It was really on the money. So, sound good? Real quick, because we're like.
What's the, do you have to use like a different value
What? Oh, like if it's an outside slab versus an inside slab? That's a worthwhile discussion. We can address that later, but we're mainly talking about interior floor slabs and structures. So yeah. Y'all are excited about this steel.
We're still having class.
So,
I didn't even check the time today.
all right. Any other quick questions? All right, hold on. I got one quick thing to say. That is it for exam 1. Everything from here on out, we're in exam 2 land. That's all I got. I'll see you all in 10 minutes because everybody's in steel. So.